summer of 1978, staff from the University of Missouri Rolla, Rock Mechanics and Explosives Research Center contracted with the in-situ gasification group, the Sandia Laboratory, to develop a drill for water jet drilling of coal seams. The ultimate objective of the program was to develop a device which would go down a conventional gasification well bore from the surface to the seam and then drill 50 feet out horizontally from the bottom of this borehole to the next adjacent well. In order to initially determine what problems would arise using high-pressure water jets to drill such a hole, the university group first went to a coal mine in the north-central part of Missouri where a simple horizontal drilling rig was set up. The unit used was self-sufficient, power being supplied by a 200 kW generator. This, in turn, powered a 150 horsepower high-pressure pump which would deliver 22 gallons of water per minute at 10,000 psi pressure. The drilling device was a modified hydraulic drilling stack which was located on two ties and held in place with a rebar driven behind the track. This was all that was used to stabilize the platform, since there was very little force exerted by the drill on the sash during the drilling process. Two hydraulic motors were used to power the drilling sash, one driving a sprocket and chain arrangement for the rotation of the drilling rod, while the second, underneath the drill sash, drove a toothed sprocket which in turn engaged the chain running the length of the sash which pulled the drilling rod forward. High-pressure water was fed to the drill through a half-inch internal diameter rubber hose. It then passed through a modified rotary coupling connected to a second high-pressure hose confined within a 2-inch water pipe which made up the drill rod. The studs driven through this pipe are to hold the hose and to ensure it rotates with the water pipe, which is in turn rotated by the sprocket and chain drive and the hydraulic motor. Nozzles were attached to the front of the drill steel through a solid connection on the pipe into which the hose was screwed. Various designs of nozzles were tested during this trial program. For the experiments which you will see, a modified UMR nozzle was used based on its design previously proven successful in drilling rock. The equipment was brought up to pressure and was initially advanced relatively slowly into the coal face. Pressure was maintained at approximately 9,000 psi at the pump, which, due to coupling friction, meant that a pressure of approximately 8,000 psi existed at the nozzle. The advance rate was slowly increased until a speed of 4 feet per minute was achieved, and this was held relatively constant for most of the drilling program. Once the drill had advanced into the coal, the forward support on the sash had to be released, since the pipe rested on the floor of the hole that was created. The coal fragments coming out were relatively large in contrast with other forms of drilling, and, of course, there is no dust with this method. After the first 12-foot length had been drilled, the pipe was broken and the inner assembly can now be seen. The outer pipe is merely used to give support to the high-pressure hydraulic hose and to provide a rotatable member. Inside the pipe, the half-inch ID high-pressure hose is also broken and the drill platform retracted so that a second 12-foot length can be inserted. The pipe is reattached to cover the new length of hose and the drill restarted. Again, 4 foot per minute advance rates were generally maintained, although, due to the large size of the hole and the slow flow of water out of the hole as the depth increased, it was necessary to reverse the drill a number of times to aid in flushing the debris. A total of 4 lengths of drill pipe were ultimately connected to make a total drilling length of 48 feet, which, with the initial 2-foot length at the front of the nozzle, gave a total drilling length of some 50 feet. At the end of the hole, the advance rate was increased to determine the maximum possible speed of advance, which was found to be 12 feet per minute. The pipe was then broken, and the 50-foot length was drawn from the hole. No problems were encountered in drilling this hole, which took less than 2 hours to drill, including the time for pipe length changes, and left the hole approximately 8 inches in dimension. The results of the first test were extremely promising, and a rig was therefore developed which would demonstrate the concepts to be used in drilling the horizontal holes out from the vertical well. For the first experiment, the drill was located at the side of the coal seam, the drill rod was fed up over a wheel at the top of a support mast, and then down through a yellow cylinder which simulates the borehole case section to the drive mechanism. A jack at the bottom of the assembly was then used to raise the drive mechanism into the horizontal position, ready to drill forward. A drilling head is attached to the front end of the drilling steel. This comprised a rotating nozzle contained on the end of the drive head. The nozzle is rotated by a hydraulic motor located in the lower compartment of the drilling head, and rotation of the nozzle is allowed by a high-pressure coupling which is contained within the body of the drill. High-pressure fluid to the nozzle and to the hydraulic motor is supplied by 3 hydraulic hoses which feed through the drill pipe. This supply pipe is flexible and is made up of 18-inch lengths of box steel hinged together, allowing flexibility. The 18-inch lengths which contain the pipe are hinged on their top surface and have a length of chain welded between the 2 hinge points. This chain engages in a toothed sprocket on the front end of the drive mechanism. The sprocket itself is driven through a shaft by another chain and sprocket drive from a hydraulic motor mounted within the well casing. The tests were carried out at 10,000 psi pump pressure, although again there was sufficient friction loss in the head and in the supply pipe that perhaps only 8,000 psi was achieved at the nozzle. For the initial test, a dual orifice nozzle, 5 degree, 15 degree divergent, was used, with the nozzle body itself rotating axially within the drilling head. While a higher speed of advance was achieved while the head was advanced up to the face of the coal, the advance rate was lowered to 18 inches per minute once the drill entered the coal seam. This was to ensure that the water jets touched the dimension of the drilling head. This required that the hole be approximately 8 inches in size. In a later experiment at another site, the drill broke through to the surface, and it was found that the hole was drilled up to 12 inches wide, although only 8 inches high. A problem with the rotary coupling within this drilling head led to a change to a second head with a slightly different design. The second head rotated so that the nozzle itself turned eccentrically around the axis of rotation, and a single orifice jet was used. This cut a slightly larger hole in the coal than the first design effect. It again was advanced forward at 18 inches a minute approximately. Both these trials demonstrated that it is possible for a high-pressure water jet system to, as it were, drill around the corner, since in both cases The supply pipe to the drilling system was fed from the vertical down through the drive mechanism at the bottom of the vertical shaft and then forward into the coal horizontally. However, it was not possible, on the occasion that this film was made, to satisfactorily drill the full 50 feet due to an equipment malfunction. At a later date, and in an event which has been recorded on videotape, it did prove possible to drill the full 50 feet with a drill stem that went through a 360-degree rotation prior to entering the drill hole. This work, which was completed in the fall of 1978, indicates the clear practicality of interconnecting two adjacent vertical wells using a high-pressure waterjet drilling device. In these tests, advance rates for such a system of 18 inches per minute were achieved.